The Akashi Kaikyo Bridge in Japan is the world's longest suspension bridge. It spans a waterway 4 kilometers wide and is designed to withstand powerful typhoons, tsunami, and earthquakes. It is the pinnacle of bridge engineering. The Akashi Bridge owes its success to 7 key inventions found in these 7 landmark bridges. At the heart of each bridge lies a major technological innovation that allowed engineers to span ever wider chasms. One by one, traveling up the scale, we'll reveal the incredible stories behind these structures and the inventions that allowed them to grow ever longer. 7 ingenious leaps forward that enabled bridges to evolve from big to bigger into the world's biggest. The Akashi Straits in Japan is one of the world's busiest waterways. It links Kobe on the mainland with Japan's densely populated outer islands. To create a bridge long enough and strong enough to span this gap, the Japanese pushed technology to its limits. To understand how the Akashi Bridge got to be this long, we need to wind back in time and scale to look at how bridge design evolved. Our journey begins in 18th century England, with a bridge just 30 meters long, built from a new wonder material. In 1779, the Industrial Revolution is in the midst of transforming England. But here in rural Shropshire, the physical barrier of this river halts its progress.
It's hard to believe, but this quiet river valley was once the very heartland of industrial Britain. The trouble is that the industrialists were over here, and a lot of their raw material was over there, in between the deep, fast-flowing River Severn.
But the ferry just couldn't cope with the explosion in traffic of people and goods.
The answer was build a bridge, but it wasn't going to be easy.
The river's only 30 meters across, but this was a critical distance for the bridge builders of the time. The conventional way of spanning such a river was to build a stone arch, a method used since Roman times. But 30 meters is about the limit this type of bridge can straddle. To make a stone arch wider, it must also be made higher to preserve the semicircular shape that provides its strength. But enlarging the arch comes at a cost. To double its size, the bridge builder must use 8 times the amount of stone. But the arch cannot bear this extra load, and the bridge collapses under its own weight.
So, how could you build a bigger and better bridge? Well, one answer would be to find a brand new material, one that was as strong as stone and could carry the same sort of weight as stone, but was itself much lighter and much easier to handle.
A promising material is already being used at the time to make small objects like kitchen utensils. It's formed by heating iron ore until it turns into a liquid.
Out pours the white-hot molten metal into your mold. It cools, leaves a shape behind. It's a magical process.
The result, a magical material called cast iron. But at this time, cast iron is unsuitable for bridge building. The coke that fuels the furnaces contains impurities that makes the iron too brittle. Then, at an iron foundry in the county of Shropshire, workers discovered that the local coke is wonderfully pure. This produces an iron as strong as it is versatile.
You could make anything. You could make machines, you could make steam engines, you could even make bridges.
And this is exactly what the foundry does to advertise the quality of its high-grade cast iron. In 1779, they set about building the world's first cast iron bridge. It's constructed from 1,700 precast sections of iron. 5 semicircular ribs form the bridge's 30-meter-long central arch. Because the structure is comprised of an iron lattice work rather than solid stone, the bridge weighs in at just 380 tons. They name it Iron Bridge. Surprisingly, it has the look of something made from wood.
It is a truly amazing structure, and yet, in its essence, it's really quite simple. You see here, recognize that it's a dovetail joint, exactly the sort of thing you'd find in a piece of joinery. This was woodworking on a grand scale using iron instead of timber, but it worked. It was a huge success.
Iron Bridge's legacy is still evident in the record-breaking structures of today. When Japanese engineers plan the biggest suspension bridge in the world, they know they must find a way to keep it as light as possible. So, like Iron Bridge before it, they construct the Akashi Bridge from prefabricated components arranged in a lattice work. And yet, this lightweight structure still contains over 250,000 tons of steel. However, steel has a major drawback. It rusts. Structural engineer Professor Alan Burden knows this bridge's vulnerabilities.
Typhoons pass through each year, and the marine environment makes corrosion a major issue for the whole structure.
To safeguard the bridge, robot watchmen, guided by remote control, look for evidence of corrosion. They can call in robot painters to patch up damaged paintwork. Beneath the bridge hang 3 gantries. These allow ordinary mortals to carry out maintenance work from below without interrupting the flow of traffic. Iron Bridge proves that by using iron rather than stone, engineers can build their bridges beyond 30 meters. But to straddle the 177-meter Menai Straits will take someone with a touch of genius and an idea borrowed from ancient history. In the 19th century, the Menai Straits in Wales forms a formidable obstacle for people travelling to Ireland. The engineer given the job of spanning this treacherous waterway is Thomas Telford, a 62-year-old self-taught Scot.
By the time he arrived at Menai, Telford had a reputation as one of the finest civil engineers in Britain. He'd been given this huge job to improve the main coaching route between Britain and Ireland.
Telford considers constructing an arch bridge from cast iron. But he would have to use scaffolding to support the arch while it's being built. This would block the movement of ships along the busy waterway. The planners don't accept this, so Telford goes back to the first principles of bridge design. Rope bridges have been used to cross rivers since ancient times, and mountaineers like Mark Handford still use them today.
So the most crucial thing in any form of bridge, is the anchor point. So we've got the tree as a solid anchor. Without these anchors, the whole bridge is going to collapse. 2, 3, 2, 3, 2, 3.
Next, they pull the ropes taut.
2, 3, 2, 3. Stop. Hold it there.
The bottom rope carries the load. The top ropes are for holding onto.
Once you get a stringers on, it'll be great.
These are really good now.
Yeah, cool. It'll self-support then.
Tying them together forms a rudimentary suspension bridge. It's fine for soldiers, but would hardly do for the London to Dublin stagecoach. Adding planks of wood to form a deck makes the bridge easier to cross. And iron chains allow it to carry heavier loads, but the deck still sags. To build a truly modern suspension bridge, the engineers must find a way to flatten the sagging deck. The answer is to suspend it from stone towers. Then extend the ropes downwards to level the deck. Telford now has a design that can bridge the Menai Straits. But he still has the problem of securing the chains at each end.
Do you think of pulling down that chain, it's going to give unless it's really firmly anchored. And that was Telford's challenge.
Somehow, Telford must anchor the chains not to the trees, but deep into the rocky banks on either side of the straits. To do so, workers blast their way through the rock to create an 18-meter-long tunnel. At the end of the tunnel, they position strong iron frames. The end of the chains thread into the tunnel and are secured to the frame with 3-meter-long bolts. Metal braces wedge the bolts and frame firmly into the cavern. The only way this anchorage can fail is if the rock gives way. Telford triumphs. The new bridge helps reduce the journey time from London to Dublin by 9 hours. His anchorages have held the 177-meter deck in place for over 180 years. Today, it still carries thousands of vehicles every week. As the first great modern suspension bridge, it shines a light on the future. In Japan, engineers face an even greater challenge when anchoring the Akashi suspension bridge. Instead of chains, the Akashi uses colossal cables. But unlike Menai, there is no solid rock to secure them into. so they must build an anchor point on the shoreline. First, they dig a hole for the foundations, a very, very big hole, and fill it with over 230,000 cubic meters of concrete. Next, they ship in mammoth metal frames. These frames will anchor the bridge cables and must be firmly secured. So they set the frames in concrete. They cast the concrete in 5 separate blocks. The gaps between the blocks allow heat to dissipate so the concrete doesn't crack. Once set, they fill the gaps to make a solid concrete block, over 50 meters high.
It also extends about 60 meters below the ground. So in fact here we have something which is more like an iceberg. You can only see the tip of what is actually going on.
Telford's suspension bridge across the Menai Straits introduces bridge designers to a new approach to building big. But in 1851, when American engineers are challenged to span the 250-meter-wide gorge at Niagara Falls, their suspension bridge would have to carry a 300-ton train. So strength becomes as big an issue as length. The massive chains on bridges like Telford's may look unbreakable, but any chain is only as strong as its weakest link, as one tragic accident would prove. In 1845, 300 people crowd together on a suspension bridge in the English town of Great Yarmouth. They gather to watch a circus stunt, a man in a barrel pulled by geese. As he approaches, the crowd cross to one side of the bridge for a better view. But the sudden shift in weight overburdens the chain. It snaps, and the deck plummets into the river. 79 people drown. Six years later, the engineers charged with bridging the Niagara Gorge need something stronger than an iron chain to support their deck, particularly since their bridge must bear the extra weight of a train. They know that iron can be made stronger if it's drawn out into a long, thin string of wire.
Stretching a material, turning it into a fibre or a wire, aligns the internal components within that material. You can get an impression of what's going on by looking at something like cotton wool. If I just pull the ball apart, you can see that strength is very, very low. If, during a manufacturing process, I'm able to take that cotton wool and align the constituents, I can make something called a thread. This is considerably stronger.
To find out just how much stronger, Dr. Wojcik stretches a metal rod to its breaking point. Then he compares it to a metal thread of the same dimensions formed from wires wound together.
The results have shown that the rod broke around about 350 pounds of force, and the wire was much stronger at around about 450 pounds of force.
The Niagara engineers work out that a cable made of over 3,500 wires would be strong enough to hold up the bridge and train. But at 900 tons, the cable is far too heavy for workers to lift into place. The solution: send the cable across 2 strands at a time. Engineers feed a loop of wire through a pulley and pull it across the gorge. Once it reaches the other side, they tether the wire to the anchorage. Then they send the pulley back to pick up another loop of wire. After 1,820 trips, they've formed an iron cable 3,640 wires thick. It takes 4 of these to hold up the bridge. In 1855, the Niagara Bridge opens to carry its first train from the United States to Canada. Although the bridge has since been replaced, the idea of using cables to support the deck lives on. Today, the cables on the Akashi Bridge are strong enough to support the weight of 90 Niagara bridges.
I'm standing next to a section from the actual cable used on the Akashi Bridge. It's over 1 meter in diameter, and you can see it's made up of thousands of small wires.
To get the wires from one bank to the other, they first fly a helicopter across with a pilot rope. Then they haul across the first bundle of 127 wires. They shuttle 290 individual bundles from one bank to the other until there's enough to form the colossal cable. Each cable weighs about 25,000 tons and contains enough wire to circle the globe 7 times. Stronger cables allow engineers to build bridges with longer, unbroken spans. But in waterways too wide to bridge in a single span, supporting towers have to be sunk into the river bed. In 1874, engineers plan a mighty bridge to join Brooklyn with Manhattan. The challenge is to anchor piers in the rushing water below. In the 19th century, New York is one of the fastest growing cities in America. But its rapid expansion is all happening within the confines of an archipelago. And long before the skyscrapers, there is a need for the island of Manhattan to be serviced by workers who live in the neighboring areas. So they have to build a bridge that will cross the 600-meter wide East River. This is too far to cross in a single span, so they're forced to build the piers in the river. This fast-flowing stretch of water runs over 9 meters deep on the Manhattan side. On the riverbed, layers of silt and sewage lie above the bedrock. This sludge is an unstable foundation for any towers built on it. To dig through it and into the bedrock below, the men must work 24 meters underwater. Engineers come up with a solution. It's called a caisson. This is a giant upturned box that they construct from wooden planks. It's designed to sit on the riverbed and provide working space for 125 men. Its walls taper down to form a sharp cutting edge designed to slice through the silt. They build the caisson on dry land. Then powerful tugs tow it out into the river. Engineers then sink it to the bottom by weighing it down with tons of granite blocks. But before men can work in it, the caisson must be drained and the water prevented from flooding back in. Engineer Peter Sluska explains.
This is a simple representation of a caisson. Imagine it being floated out into the river where the towers needed to go. once it was sunk down to the river bottom and was completely filled with water, the pneumatic system was installed in the form of a pump, and air was pumped into the caisson. And as air is pumped in, the water, you can see, is being pushed out through the bottom. Once all the water is pushed out, men were able to go down inside the caisson and excavate underneath it.
13 huge compressors pump the air in to keep the river out. The men can breathe, but the environment within is deeply unpleasant.
Working in the caissons was really quite a terrible experience. It was constantly hot, it was constantly moist, the work was backbreaking, and it was just excruciatingly hard and tedious work.
Worst of all, they work in constant fear of drowning and the caissons becoming their tomb. The air pressure must be kept up to stop water breaking in through the walls. So now the problem becomes how to get men in and out. If they open a hatch, it will break the pressure seal. Air would escape and the river would flood in, drowning the miners. To solve this problem, the engineers install airlocks. Only one door at a time may be opened to maintain the vital air pressure. Once the miners are sealed inside, fresh air replaces the compressed air, and the men can safely surface through the top hatch. When the workers get right down to the bedrock, they start filling each caisson with concrete. The caissons now form the foundations for the mighty towers above. On the 24th of May, 1883, Brooklyn Bridge is born. Its towers dwarf most other buildings on the New York skyline of the day. By uniting Manhattan with Brooklyn, the Great Bridge unites the metropolis with its workforce and helps create modern New York City. Every day, the Brooklyn Bridge carries over 140,000 vehicles and thousands more pedestrians. To this day, the Brooklyn Bridge remains an engineering masterpiece, as vital now as it was over a century ago. But engineers working on Japan's Akashi Bridge face an even greater challenge. The foundations for the towers supporting their bridge must be laid in waters far deeper than New York's East River. They must put them 60 meters down in the Akashi Straits. Technological advances now allow for huge dredges to dig out the seabed foundations instead of risking the lives of miners. But the Japanese still use caissons to form their foundations. The caissons stand 70 meters tall and 80 meters wide, but they're made of steel rather than wood. They're so large, they require 12 tugs to tow each one into position over the excavated seabed. Each caisson has an outer and inner wall. The gap between the walls forms a circular compartment filled with air. This keeps the caisson buoyant. To sink it, engineers flood this compartment with seawater. Once it's located on the seabed, they displace the seawater in its central chamber by filling it with wet concrete. This special concrete keeps its cohesion in water. Finally, they place a concrete lid on the caisson, and the pier is complete, ready to form the base for the tower. Caissons allow bridge builders to go longer by digging deeper. But when challenged to span the 1.6-kilometer wide Golden Gate Strait between the city of San Francisco and neighboring Marin County, they must find a way to build taller as well. The strait is notorious for its extreme weather conditions. This makes crossing by water dangerous. But this doesn't deter people from trying to ferry their cars across. In the decade following World War I, the traffic in the Bay Area increases sevenfold. The ferries can no longer cope. So in 1933, engineers planned the world's longest suspension bridge. In any such bridge, the best balance of forces is achieved when the cables are set to form a particular curve. To preserve this shape, engineers wanting to lengthen the roadway must also raise the height of the towers.
You move from a relatively short suspension bridge to a relatively long one, and the towers need to get taller, pretty much directly proportional to the length of the bridge. So you make twice as long of a bridge, and the towers need to be roughly twice as tall.
But this creates an immensely complex engineering challenge. The 1,280-meter span requires engineers to hang cables from points 152 meters above the deck. This calls for towers 227 meters tall. But slender stone towers will buckle under the weight of the load. Another option is to build thicker towers. But any stone tower capable of resisting the buckling requires a base nearly 50 meters wide. This would obstruct the passage of ships and compromise the aesthetics of the bridge. This bridge needs a stronger and lighter material for its towers. Rather than use stone blocks, builders opt for steel plates. 4 plates join together to form a shaft 11 meters tall. These make strong building blocks, far lighter than solid steel. Clustered together into cells, they form a sturdy honeycomb structure. A crane lifts the cells into place. Once it completes each section, the crane hoists itself up and begins again. Because they are hollow shafts rather than solid stone, the towers can be kept slender from top to bottom, and the steel allows the towers to flex instead of buckle under the strain from the cable. But as the towers rise, so do the risks. Someone must lock the cells together and install the rivets, over 1 million of them. The ironworkers risk life and limb, hanging off the towers exposed to the vicious Pacific storms. For the first time, bridge builders wear hard hats, face masks, and use safety lines. A huge net saves 19 of the ironworkers from lethal falls. But despite the precautions, 11 men give their lives for the bridge. The towers rise above the bay, tall and slim, and strong enough to support over 50,000 tons of deck and cable. The bridge is a testament to the strength of steel and how it allows engineers to build ever higher. And in an era that saw steel-framed skyscrapers like the Empire State Building break records, the Golden Gate Bridge towers were the tallest structures west of New York. The tallest towers on any suspension bridge today belong to the Akashi Bridge in Japan. At 300 meters, they stand 70 meters taller than those of the Golden Gate Bridge. Each is comprised of 30 sections. Engineers grind and polish the top and bottom surface of each section until they are perfectly flat. This means that when cranes stack the sections one on top of the other to form the 100-story towers, they will be precisely vertical. Their internal honeycomb structure makes them light and strong.
Well, I'm just climbing up, actually through the inner structure of one of the main towers. These pieces of steel are joined together in the shop using welds. You can see some of the weld beads here and here. And the joints on site are made using bolts.
Advanced robot welding techniques combine with 1.5 million good old-fashioned bolts to hold the towers together. Building taller allows suspension bridges to span greater distances. But as their decks get longer, they're also more likely to twist and bend. They must now be designed to resist a particularly destructive force of nature: wind. In 1940, a new bridge opens across the Tacoma Narrows in Washington state. But it has a fatal flaw. In a modest wind, the deck begins to move up and down. Then it starts to twist. Finally, the bridge collapses. Engineers now understand why the structure failed.
Aerodynamic instability has to do with the shape of the structure that the wind encounters as it blows across the bridge.
A bridge deck with a flat side presents an obstacle to the wind. When a crosswind hits it, the flow of air is disturbed, causing eddies to form above and below the deck. These produce areas of varying pressures that either suck the deck up or push it down. Once the deck moves, the bridge flexes against it.
The wind and the structure's movement actually interact with each other. It becomes a self-exciting phenomenon. It will build up the amplitude to the point where it will wreck itself, just as Tacoma Narrows did.
One solution is to introduce a more streamlined profile to the sides of the deck to slice through the wind and channel it harmlessly over and under the roadway. In 1946, engineers consider using such a design for a new, even longer bridge. They have to span the 1.6-kilometer wide entrance to New York Harbor across the Verrazano Narrows. They expect the crossing to be so busy that the bridge must be able to accommodate 12 lanes of traffic split across 2 decks. But the engineers know that streamlined edges on a double deck might not channel the wind safely away. Instead, the streamlining could cause the currents of air to collide and produce further disruption. So rather than deflect the wind, they decide to resist it by stiffening the deck so that it can't twist or bend. The most effective way to do this is to enclose the decks in a great box. But they know a 2-kilometer-long steel box would be too heavy for the bridge's cables. Instead, they take thin steel bars and assemble them into a lightweight skeletal unit. 75 of these lock together to form a massive open latticework of steel. This allows the wind to flow unimpeded through the structure. This unique design resists the powerful Atlantic storms and supports 12 lanes of traffic. Its twin decks carry almost 200,000 vehicles a day from Brooklyn and Queens to Staten Island and on to the main Atlantic highway system.
It's a remarkable achievement. This bridge supports 70% more load than the Golden Gate Bridge, which of course was its nearest equivalent at the time.
When completed in 1964, the Verrazano Narrows Bridge becomes the longest and heaviest suspension bridge in the world. The bridge marks the gateway to New York Harbor and stands today as one of the city's landmark structures.
The Verrazano Narrows Bridge, I think, is the culmination of a great era of American bridge building, and of course the biggest and the greatest of them all.
And the design is so good that over 30 years later, the Japanese used the same open box concept to stiffen the deck of their Akashi Bridge.
I'm standing at the moment within the stiffening girder of the bridge. You can see it's primarily triangular in geometry, a latticework of steel members. It is also very light, and the whole makes up a box structure, which is very difficult to twist.
But the Akashi Bridge faces another challenge. It stands in a notorious typhoon alley. Japanese engineers must ensure the Akashi Bridge can withstand the worst nature can throw at it. So they build one of the world's biggest wind tunnels to explore its design limits. Even at 100th scale, the model of the bridge measures 40 meters. Huge fans generate the equivalent of 300-kilometer-an-hour winds, so the engineers can test and refine their design.
By using wind tunnel test, the engineers were able to devise a structure which would both minimize the load generated by the wind and also be stiff enough to resist any loads which the wind would cause.
The wind tunnel tests suggest they need to deflect the wind as well as stiffen against it. So they insert a massive steel beam just below the roadway. When a strong crosswind hits the beam, it gets redirected upward through a grill in the deck, neutralizing its destructive effect. The 1,900-meter steel spine works with the reinforced deck to ensure the Akashi Bridge can withstand typhoon winds of up to 300 kilometers an hour. The Verrazzano's wind-defying capabilities enable bigger bridges to safely straddle increasingly exposed crossings. But to build the world's biggest suspension bridge, engineers must defeat a force of nature powerful enough to shake the structure's very foundations. Japan is situated in one of the world's most seismically active areas. In 1923, an earthquake devastates Tokyo, killing over 100,000 people. Hundreds of tremors hit the country every year. The unstable ground makes Japan the last place on Earth an engineer would choose to build the world's longest suspension bridge.
If the ground beneath a suspension bridge is shaken by an earthquake, we could, in the worst case, for example, get a tower toppling over, obviously a catastrophic event.
The first line of defense against an earthquake is the bridge towers themselves. They're built from steel to make them flexible. If a tremor hits, the steel towers can move with the earth to absorb the shock. And inside each tower lies a second layer of protection, 20 huge pendulums called dampeners. Each 10-ton dampener hangs from a frame. If a tremor causes the tower to lurch one way, the huge hydraulic dampeners swing in the opposite direction, counteract the shift, and prevent the tower from falling over.
Now, in these two models, we can compare the effect of fitting a damper. The tower on the left is a normal tower with no damper. The one on the right has a damper fitted to the top. And we can see how much each one sways by observing the arrows at the back. It's clear from this model test that the tower without the damper on the left is swaying more than the tower with the damper on the right.
To test the dampeners in the absence of an earthquake, engineers resort to a novel approach. They carefully choreograph more than 100 workers to sway in perfect harmony to mimic a tremor. During this man-made quake, the dampeners react to keep the tower steady. But on January the 17th, 1995, nature tests the technology for real. A magnitude 7 earthquake devastates Kobe, the city on the Akashi Bridge's north bank. It kills over 6,000 people and destroys more than 100,000 buildings. But the Akashi Bridge survives, saved by its dampeners. It still bears the scar of that fateful day. The earthquake opens a fault line in the seabed directly under the bridge. This causes the ground and bridge towers to shift apart and stretches the bridge by over a meter. Engineers must fill this space with extra decking to join it to the shoreline.
As a result of this earthquake, the longest bridge in the world became a little bit longer.
The Akashi Bridge proves the strength of its record-breaking design in the most challenging environment. It is the culmination of over 2 centuries of innovation and engineering breakthroughs. After more than a decade of operation, it remains the longest and tallest suspension bridge in the world.